Hi everyone, how are you all? So in this lecture, we will study Cantor's theorem, and this is very important theorem. We will see. Okay, so let's start. So far, what we have seen in countability in this chapter, countability, we have seen the definition of cardinality, all the results related to cardinality. Those we have seen. We have seen the definition of countable set, uncountable set. Also, we have seen Cantor's diagonalization proof. Okay, this also we have seen. Now, we have also seen three definitions of countability, also theorems for countable set. Okay, so these are the things, these are the concepts that we have seen so far. Okay, now in this lecture, we are going to study Cantor's theorem. Okay, so before we start, let me tell you, this Cantor's theorem is extremely useful theorem to solve many questions. Okay, we will take all the questions, but I am saying that this theorem, this is extremely useful to solve lots of questions. Okay, so understand this theorem very clearly. Okay, now let's start. So before we start, let's revise some definitions which we need for this Cantor's theorem. Okay, so let's revise some definitions. Let's revise. So tell me, tell me the definition of cardinality of A is equal to cardinality of B. When can you say? Tell me. When can you say that cardinality of A is equal to cardinality of B? See, A comma B, they are two set. They can be any set. Remember, they can be any set. They can be finite, infinite, countable, uncountable, whatever. See this. See this. Okay, they can be finite, infinite, countable, uncountable, whatever. So whatever two set you take, okay, any two set you take, when can you say set A cardinality is equal to set B cardinality? If and only if there exists a bijection between A comma B. Yes or no? I can say if and only if there exists a bijection. If and only if there exists a bijection between A comma B. Okay, there exists a bijection between A comma B. So this is the point, right? Set A cardinality is equal to set B cardinality if and only if there exists a bijection between A comma B. Okay, so this is the idea. Or I can say there exists a bijection from A to B. This also I can say. Okay, there exists a bijection F from A to B. From A to B. Okay, so this is the definition of same cardinality. When can you say two set have same cardinality? Remember, these two set, they can be finite, infinite, countable, uncountable, whatever. So any two set you take, when can you say they have same cardinality? If and only if there exists a bijection between A comma B. So this is the definition. Tell me the answer for this question. What the definition of this equation? Set A cardinality is less than equal to set B cardinality. What the definition of this equation? So when can you say set A cardinality is less than equal to set B cardinality? When there exists an injection from A to B. Very good. Okay. So this will happen if and only if there exists injective function. This will happen if and only if there exists an injective function F. Injection F from A to B. From A to B. Okay. This will happen. So very simple. There must exist injective function from A to B. Then you can say that set A cardinality is less than equal to set B cardinality. Now tell me the answer for this question. Now let me know the definition of this. Set A cardinality is strictly less than. Set A cardinality is strictly less than set B cardinality. If and only if, when this will happen? When this will happen? So this will happen if there exists an injection from A to B, but there is no bijection between A comma B. Yes or no? This will happen if and only if there exists an injection from A to B, there exists an injection from A to B, there exists an injection, but there is no bijection. But there is no bijection between A comma B. But there is no bijection between A comma B. Between A comma B. Yes or no? Okay, is this clear? See, very simple. When can you say set A cardinality is strictly less than set B cardinality if and only if there exists an injection from A to B, but there is no bijection between A comma B. There is no bijection between A comma B. Okay, so this is the definition. So this is important definition. You can just see this slide, very nice slide from Stanford University. You can see set S cardinality is strictly less than set T cardinality. When can you say set S cardinality is strictly less than set T cardinality? If this happens and they don't have same cardinality, right? Yes or no? Okay, yes or no? Very simple. So I can say that it's like this. See, this is like this. When can I say A is less than B? A is less than B if and only if A should be less than equal to B and A should not be equal to B. Okay, the same thing is happening here. The same thing is happening here. You can see that set S cardinality is less than set T cardinality if and only if this will happen and they don't have same cardinality. They don't have same cardinality. That means there is no bijection. Okay, that means there is no bijection. There is no bijection. And set S cardinality is less than equal to set T cardinality. That means there is injective function from S to T. Okay, so this is the definition. You can see this is the definition. Now let's move on now. Now let's move on. Now let's see this question. Tell me the answer for this question. Think about it and give me the answer for this question. Let S be a finite set. S is a finite set, remember. Okay, S is a finite set. Is it always true for every finite set? Is it always true for every finite set that cardinality of S that is strictly less than cardinality of PS? Can I say? Let me know. S is a finite set. Now, is this true for every finite set that cardinality of S that is strictly less than cardinality of power set of S? What is power set of S? For any set, tell me, for any set S, what is power set of S? What is power set of S? Let me know. This is called power set of S. What is the definition of power set of S? Power set of S. That means set of all subsets of S, right? Yes or no? That is set of all subsets of S. This is set of all subsets of S. Very simple. So power set of S, what is that? Power set of S, that is set of all subsets of S. Set of all subsets of S. Okay. So very simple. Now you tell me, is this statement true? Is this statement true? That cardinality of S that is strictly less than cardinality of PS for every finite set. Is this statement true? The answer is yes. Yes, this statement is true. Yes, this statement is true. Is it always true? The answer is yes. The answer is yes. For every finite set, this will be true. You can check any finite set. First of all, you tell me, for finite set, what will happen? See, this you already know. For a finite set S, what is the cardinality of power set? For a finite set S, tell me the cardinality. What is the cardinality of power set? How many subsets are there? How many subsets are there? Tell me, for a finite set S, what is the cardinality of power set? That is 2 power cardinality of S. 2 power cardinality of S. Yes or no? Very simple. This is the number of subsets. Remember, this is the number of subsets of S. This is the number of subsets of S. And this is the cardinality of power set. That is 2 power cardinality of S. Yes or no? Very simple. Now you tell me, for example, what is the minimum cardinality possible? S is finite set. S is finite set. Let me know. S is a finite set. So what is the cardinality possible? For example, if cardinality of S is 0, then what will be the cardinality of power set of S? If cardinality of S is 0, if S is 5, okay, cardinality of S is 0, that means S is 5. Yes or no? Okay, that means S is 5. So for empty set, if you have empty set, then what will be cardinality of PS? That will be 2 power cardinality of S. That will be 1. Can you notice? Can you notice here? Can you notice the cardinality of power set that is greater than, strictly greater than cardinality of S? That is strictly greater than cardinality of S. Yes. Okay. What about if you have set cardinality equal to 1? If you have one element only, if you have one element only, if you have only one element in your set you have only one element. Now tell me what will be the cardinality of power set? That will be 2 power cardinality of S. That will be 2 power 1. That will be 2. Can you notice? Again, can you notice? Power set cardinality is strictly greater than set S cardinality. Yes or no? Is this clear? So tell me now. Now let me know. So you can easily notice for every n belonging to set of positive non-negative integers. Yes or no? for every n belonging to whole numbers, belonging to 0, 1, 2, 3, and so on. Can you notice 2 power n that will always be greater than n? Yes or no? 2 power n that will always be greater than n. For example, you can notice 2 power 0 that is greater than 0, 2 power 1 that is greater than 1, 2 power 2 that is greater than 2, 2 power 3 that is greater than 3, and so on. Okay, is this clear? For every n, you can see 2 power n that is greater than n. Now you tell me again, is this statement true for every finite set? This statement, S is a finite set, S is a finite set. Is it always true for every finite set? Cardinality of S is strictly less than cardinality of PS. Cardinality of S that is strictly less than cardinality of PS. Yes, this statement is true. Yes or no? Is this clear? This statement is true. This statement is true, right? Yes or no? So this is the simple point. You can see if you have finite set S, if you have finite set S, okay, let's assume cardinality of S that is N. Okay, cardinality of S that is N. Okay, because this is a finite set, so this cardinality belongs to whole numbers. Okay, you can see because this is a finite set, so cardinality of S that is some whole number, some non-negative integer. Now you can easily notice what will be the cardinality of PS. That will be 2 power cardinality of S, that will be 2 power n, and that is greater than n. That is greater than n. Okay, that is greater than n for all n belonging to whole number. Okay, for all n belonging to whole number, right? Yes or no? So that's the point. So I can say this is the conclusion. So we can say for every finite set. So for every finite set, whatever finite set you take. So for every finite set S, what will happen? The cardinality of power set that will be strictly greater than cardinality of S. Yes or no? This is the result. This is the simple result. For every finite set, this will happen. Whatever finite set you take, this will happen. So you can easily see here, for example, if you have set S with cardinality true, then how many elements will be there in the power set? If your set has 2 elements, then how many elements will be there in the power set of S? There will be 4 elements. You can notice empty set. Okay, this one, this one, this one. These are the subset of S. You can notice all of them. These are the subset of S. So you can see the cardinality of S that is 2, but the cardinality of PS that is 4. So you can see cardinality of S that is strictly less than cardinality of PS. If you take a set with 3 elements, then also the same thing will happen. If you have a set with 3 elements, then the cardinality of power set that will be 8. Again, you can notice cardinality of S that is strictly less than cardinality of PS. Again, you can notice if you have a set with 4 elements, then also what will happen? Then also you can notice the cardinality of power set that will be 16. Again, you can notice cardinality of S that is strictly less than cardinality of power set. Okay, so this is the simple result. If you have any finite set S, then what I can say cardinality of power set that will be strictly greater than cardinality of S. Yes or no? Is this clear? Please tell me. Is this point clear? Let me know. So very simple, right? Yes or no? Okay, let's move on now. Now tell me, if I give you any set, countable, uncountable, finite, infinite, will this statement be always true? The same statement, see the same statement that cardinality of S that is strictly less than cardinality of PS. This same statement, is this always true for any set? Remember, S can be any set. S can be finite, S can be infinite, S can be countable, S can be uncountable, whatever. S can be any set. S can be any set. So can I say, is this statement always true for every set S? Is this statement true for every set S? And the answer is yes. And the answer is yes. And this is called Cantor's theorem. This statement is called Cantor's theorem. Okay. We will prove it. Don't worry. We will prove it. But I am saying that yes, this will always happen. See, the answer is yes. Means, please understand this. This is Cantor's theorem. Okay. This is called Cantor's theorem. What is Cantor's theorem? Cantor's theorem says that S can be any set. Finite, infinite, countable, uncountable, whatever. If you take any set S, then This will always happen. Cardinality of S that is strictly less than cardinality of PS. This will always happen. This will always happen. For example, let's see some example. For example, let's assume you have set of natural numbers. So tell me what you can say about the power set of n. First of all, what is power set of n? What are the elements in the power set of n? See, this is your n. What elements you have in the power set of n? Tell me. First of all, you tell me what elements you have in the power set of n. In the power set of n, you have subsets of n, right? You have every subset of n. In the power set of n, you have every subset of n. So tell me, is this subset of n empty set? Is this subset of n? Yes. Tell me, is this subset of n 4,99? Is this subset of n? Yes, this is also subset of n. Is this subset of n integers? Is this subset of n? No, this is not subset of n. Is this subset of n? N is any subset of n? Any subset of n? Yes, this is subset of n. Right? Yes or no? For example, set of all prime numbers. For example, set of all prime numbers. Okay, set of all prime numbers. This. What about this one? Set of all prime numbers. Yes, this is also subset of n, right? Yes or no? So like this. I hope you understood. I hope you understood. So in this, remember in the power set, you have every subset of n. In the power set, you have every subset of n. This is set of all subsets of n. This is all subsets of n. Okay. So very simple. This is the power set of n, set of all subsets of n. Now, what this Cantor's theorem is saying? What this Cantor theorem is saying? Tell me. What this Cantor theorem saying? So according to Cantor theorem, what will happen? So as per Cantor's theorem, what this Cantor's theorem says? Let me know. This Cantor's theorem is saying that the cardinality of n that is strictly less than cardinality of power set of n. Is this clear? The cardinality of n that is strictly less than cardinality of power set of n. The same statement I can also write like this. The same statement I can write like this. Cardinality of n that is strictly less than cardinality of, or I can say 2 power cardinality of n, right? Yes or no? Like this. Is this clear? The cardinality of n that is less than, strictly less than 2 power cardinality of n. Yes or no? Okay, so now what this means, let me know. What this statement actually means in terms of injection bijection, what this statement means. So this statement tells you that there is no bijection between n comma pn. Yes or no? This means there is no bijection. This means there is no bijection between n comma pn. Between n comma pn, there is no bijection. There is no bijection, remember. There is no bijection between n comma pn. This statement also tells you what is pn, countable or uncountable. From this statement, you tell me what is pn. Pn is countable or uncountable. Power set of n. Power set of n that is countable or uncountable. Let me know. That is uncountable. Yes or no? That is uncountable because cardinality of power set of n that is strictly greater than cardinality of n. Yes or no? Very simple. Is this clear? So this is what Cantor's theorem means. Remember, according to Cantor's theorem, you can see what will happen. For example, I can say cardinality of z, that is set of integers, that is less than, strictly less than cardinality of power set of z. Okay, is this clear? Okay, or you can understand like this, that cardinality of z that is strictly less than 2 power cardinality of z. So like this you can understand. Okay, so anyway, so again what this means? Again what this means? This means what? Tell me. This means that first of all, there is no bijection. Yes, there is no bijection between z comma power set of z. Okay, what the second thing it means? It means power set of z is what? This set is uncountable set. Yes or no? This is uncountable set. Okay, and what this means? This means there is injection from z to pz. Yes or no? There exists injection from z to pz. So this is what it means. I hope you understood. So the Cantor's theorem is this. What is Cantor's theorem? So remember the Cantor's theorem. This is very simple theorem. We will see the proof. Don't worry. Don't worry. We will prove it. Don't worry. We will prove it. Cantor's theorem says that for any set S, whatever set you take, remember for any set S, this S can be finite, infinite, this S can be finite, infinite. In the infinite, this can be countable, uncountable, whatever. Okay, this can be countable, uncountable, whatever you take. This can be countable, uncountable. So whatever set you take, for any set, what will happen? For any set, whatever set you take, what will happen? The cardinality of S, that is strictly less than cardinality of PS. Cardinality of S, that is strictly less than cardinality of PS. Okay. And what it means, let me know. So what it means? It means there is never a bijection between S, PS. Yes or no? So remember, whatever set you take, for any set S, whatever set you take, there is no bijection between S, PS. There is no bijection between S, PS. There will be never a bijection. Okay, there will never be a bijection. Is this clear? So you will never have bijection between S, PS. But you will have injection from S to PS. Yes or no? Yes or no? There exists injection from S to PS. Injection from S to PS. There exists injection from S to PS. But there is no bijection between them. So this is what Cantor's theorem says. Okay, this is the statement of Cantor's theorem, that for any set S, whatever set you take, for any set S, this will always happen. Okay, whatever set you take, you can take finite, infinite, whatever set. For example, if you take this set, let's assume you take this set till 10. Is Cantor's theorem true? For this set also, the Cantor's theorem will be true. Cardinality of S, that is strictly less than cardinality of PS. What the cardinality of S? Tell me. What is the cardinality of S? That is 10. That is strictly less than cardinality of PS. That is this. Yes or no? You can easily notice 10 is less than 1024. Because 2 power 10, that is 1024. Okay, is this clear so far? Let me know. So, very simple. Now, this is the Cantor's theorem. You can easily read the statement. The cardinality of power set of S, the cardinality of power set of set X that exceeds cardinality of X. This is the Cantor's theorem. Okay, or I can say, what is Cantor's theorem? For any set A, for any set, remember, for any set, countable, uncountable, finite, infinite, whatever, for any set A, the cardinality of A is strictly less than cardinality of A's power set. Okay, you can see this is the statement. Okay, now let's see the proof. Now what we are going to see? We are going to look at the proof, and we will prove it using Cantor's diagonalization idea. We will prove it using Cantor's diagonalization idea. Okay, we have already seen what is this diagonalization idea. Yes or no? A lot of questions we have done. Cantor's diagonalization idea. So using that idea, we will prove that this Cantor's theorem is true. This statement is true. So first of all, what we need to prove? Let's see what we need to prove. First, you understand what you need to prove. So tell me what you need to prove. You need to prove that, remember, you need to prove that for any set S, whatever set you take, finite, infinite, countable, uncountable, whatever set you take, what will happen? The cardinality of S is strictly less than cardinality of PS. This is what you need to prove. And what this means, let me know. Let me know what this means. First, you tell me what this means. When I write like this, when you write like this, what this means? What this means? This means there is injection from S to PS. Okay, what this means? This means there is injection. Okay, what you need to prove? You need to prove there is injection. You need to prove there is injection from S to PS. Correct? You need to prove there is injection from S to PS. From S to PS. And what you need to prove? What you need to prove? Tell me. And you need to prove there is no bijection between S, PS. Two things you have to prove. There is no bijection between S, PS. Agree? Agree or not? Two things you have to prove. You have to prove two things. These two things you have to prove. Okay. So this is what we have to prove. We have to prove this. Okay. There is no bijection between S, PS. And there is injection from S to PS. This is what we have to prove. I hope you understood. Okay. So remember, this is always true for every set. For every set, this is true. For any set, finite or infinite, for any set, this is true. So first we will prove for finite set. Okay, let's prove for finite set. That is very easy. Yes or no? So case one, for finite set S, the cardinality of S that is strictly less than cardinality of PS. So let's prove it. This is actually very easy. You don't have to do anything. You already know if you have a finite set S. If you have a finite set S, then the cardinality of S that will be what? Cardinality of S that will be N, which belongs to some whole number. Yes or no? If you have a finite set, then the cardinality of S that will be N, which belongs to set of whole numbers. Okay, so this N is some whole number, N is some non-negative integer. Okay, in this situation, tell me what the cardinality of PS. In this situation, what the cardinality of PS? That will be 2 power N, or I can say that is 2 power cardinality of S, that is 2 power N. Okay, so you can easily notice that this thing we already know, 2 power N that is greater than N, 2 power N that is greater than N for all N which are non-negative, for all non-negative integers. This we already know. So what will happen? So I can say cardinality of S that is strictly less than cardinality of PS. Okay, that's it. So hence proved. See, for finite set, you don't have to do anything. For finite set, remember, for finite set, you don't have to do anything. Just simply you can easily see. If I give you a finite set S, then you can easily see that cardinality of S that is strictly less than cardinality of PS. Okay, this is very easy. Yes or no? Now, interesting proof is when you prove for infinite set. For infinite set, if you have an infinite set, now when I say infinite, does it mean countable infinite or uncountable? When I say infinite, does it mean countable infinite or uncountable? Any of them, both. Okay, when I say infinite, okay, you can take uncountable also, you can take countable infinite also. Everything is covered. Every infinite set is covered. Remember, every infinite set we have covered here. So I can say for infinite set, we need to prove that cardinality of S that is strictly less than cardinality of PS. And we can prove it using diagonalization idea. This diagonalization idea we can apply. Okay. So remember what we need to prove. Just remember this. If you want to prove, if you want to show this, okay, if you want to show this statement, if you want to prove this statement, to prove this, you have to prove this statement, right? Yes or no? If you want to prove that cardinality of S that is strictly less than cardinality of PS, you have to prove that there is injection from S to PS. There is injection from S to PS, and there is no bijection between S, PS. Okay, this is what you need to prove. Remember, you need to prove this, that there is injection from S to PS, but there is no bijection between S, PS. Okay, so first we will prove that there is no that there is injection from S to PS. Okay, there is injection from S to PS. So please understand, you have infinite set S. You have infinite set S. Okay, you have infinite set S. Now this is some infinite set. I don't know. For example, this can be x1, x2, x3, and so on. Okay, this is infinite set S. Okay, this can be countable, uncountable, whatever. This can be countable, uncountable, anything. Okay, so let's assume this is your infinite set S. Now, for this set, what we need to prove? For this infinite set, what we need to prove? We need to prove this. What we need to prove? We need to prove that cardinality of S that is strictly less than cardinality of PS. This is what we need to prove. Agree? Okay. So this is what we need to prove. Now, if you want to prove this, first, two things you have to prove. Yes or no? If you want to prove this, then you have to prove two things. To prove this, you have to prove two things. First thing, second thing. What are those? The first thing is there is injection from S to PS. You have to prove there is injection from S to PS. First, you have to prove this, that there is injection from S to PS. And what the second thing you will prove? What the second thing you have to prove? That is no bijection between S, PS. Or I can say there is no bijection from S to PS. Clear? So two things we have to prove. We have to prove two things. That there is injection from S to PS and that there is no bijection from S to PS. So first we will start with the first thing. Okay. First, let's start with this thing. Okay, so let's start with the first thing. That is, let's prove that there is injection from S to PS. Okay, first let's prove this. First, let's prove. Let's prove this one. Means there is injection from S to PS. Tell me, can you prove it? Can you give me some injection from S to PS? Can anyone give me some injection from S to PS? Can you give me some injection from S to PS? Let me know. Can you give me some injection from S to PS? Please tell me. Anyone? See, very easy. Can you give me some injection? I just want injective function. I just want injective function. Injective function means different elements, different image. Yes or no? Different elements, different image. Different elements have different image. Have different image. Different elements have different image. Can anyone give me injection from S to PS? For example, just take S. S can be any set. You can take any set. For example, let's assume S is N. Okay, let's assume S is N. Let's assume. Okay, I can say for S equal to N. For S equal to N, can you give me injection from S to PS? This is your S. This is your S, and this is your PS. This is your S. This is your PS. In S, you have, for example, 1, 2, 3, 4, and so on. This is your S. And what is your PS? In your PS, you have the subsets of S. All the subsets of S. Okay, for example, you have phi also. You have this set also. You have this set also. Okay, and so on. For example, you have this set also, 1, 2. You have N also. You have set of prime numbers also. You have every subset of N. But give me one injection. I just want injective function. So yes, you can easily give this injective function. Is this injective function? Tell me. Let me know. Is this injective function or not? If I do like this. If I do like this, is this injective function or not? Is this injective function or not? Let me know. For any N, if I do like this, is this injective function or not? Yes, this is injective function, right? Yes or no? This is injective function. So did you understand what we have done? So remember, if you have for any set S, whatever set you take, for any set S, this can be uncountable, whatever. See, this can be countable, uncountable, whatever. This can be countable, this can be uncountable, whatever set you take, any set you take. What I can say, there exists an injection. There exists an injection. You can give an injective function. There exists an injection from S to PS. From S to PS, there exists an injection. There exists an injection F. What that? Tell me what that? That is like this. F of N is equal to set containing N. Yes or no? F of N is equal to set containing N. Very simple. F of N, that is equal to set containing N. Whatever set you take, in this set you can have, for example, A1, A2, and so on, whatever you have. Then I can say this is your power set of S. Then look at this. A1 goes to set containing A1. A2 goes to set containing A2. A3 goes to set containing A3. Okay, and so on. And so on. So you can see this is an injective function. Yes or no? This is injective function. Agree? For all N. Okay, Fn equal to set containing N. This is injective function. You can easily notice. Is this surjective function? This function, is this surjective function? No, this is not a surjective function. This is not a surjective function. A lot of sets are not covered. For example, set containing A1, A2, A3. Set containing A1, A2, A3. That has no pre-image. Okay, set containing, for example, phi does not have any pre-image. Yes or no? S also does not have any pre-image. There is no pre-image for S. So like this, I hope you understood. So this is the injective function. You can see this is the injective function from S to PS. So that's it. So that's it. Yes or no? So I can say, so hence proved. So we have proved. What we have proved, tell me. So hence proved. What we have proved so far? So far what we have proved? Tell me. So far we have proved that for any set S, if you take any set S, this can be, remember, this can be any set. You can take whatever set you want. You can take countable, uncountable, whatever set you want. For any set S, what will happen? I can say there exists an injection from S to PS. For any set, there exists injective function. There exists injective function from S to PS. From S to PS, there exists injective function. You can create injective function from S to PS. So this is what we have proved. So far, this is what we have proved. Okay. So very simple idea. I hope you understood. Okay. Now, what is the second thing we need to prove? Now we need to prove there is no bijection between S comma PS. Yes or no? See, we have already proved that there is injection from S to PS. Okay, this is the injection we have given, right? Yes or no? From S to PS, this is the injection we have given. Agree? This is the injection. This is the injection we have given. Fx equal to set containing X. So there is injection from S to PS. Okay, the first step is done. See, we have just finished the first step. Yes or no? This first step, there is injection from S to PS. This step is tick mark. We have done this. Now, what now? Now what? Now tell me what. Remember, this was you wanted to prove this. You wanted to prove that cardinality of S is strictly less than cardinality of PS. This is what you wanted to prove. And to prove this, two things you have to prove. You have to prove two things. The first thing was there exists injection. This we have done, right? There exists injection from S to PS. From S to PS. This we have done. Okay, I can say this we have done. Now what we need to do? Now we need to prove there is no bijection. Now we need to prove there is no bijection but from S to PS. There is no bijection from S to PS. Okay, now this is what we need to prove. Remember, this is now we prove. This is what we prove now. Is this clear? Now tell me, if you want to prove there is no bijection, what you need to do? This is what we need to prove, remember. Okay, now, please understand, this is what we need to prove. Now we need to prove that there is no bijection between S comma PS. Okay, between S comma PS, there is no bijection. So please understand that we are taking S is infinite set. Yes or no? Okay, so let's assume S is infinite set. This can be any infinite set. This can be uncountable, whatever. This is infinite set containing these elements like x1, x2, x3, and so on. This can be uncountable also, no problem. Okay, for example, this can be uncountable also, no problem. But the point is, these are the elements, let's assume. Okay, x1 and so on. So this is your infinite set. Now, what we need to prove, tell me. Just take your copy pen. We will prove it using Cantor's diagonalization argument. So what we need to prove? We need to prove there is no bijection. This is what we need to prove. There is no bijection from S to PS. From S to power set of S. This is what we need to prove, that there is no bijection. How to prove it? What is the idea to prove? To prove what we will use? Use Cantor's diagonalization argument. Yes or no? Use Cantor's diagonalization proof. Cantor's diagonalization proof. Cantor's diagonalization idea. Okay, that idea you use. Cantor's diagonalization idea. Okay, just use that idea. Now tell me, if you want to use this idea, then what you will do? In this idea, what we do? First, we assume there is bijection. Okay, first we assume there is bijection. So you can prove by contradiction. See, you can prove by contradiction. Proof. Okay, we can prove by contradiction. Prove by contradiction. We can prove it by contradiction. So first what I will assume, let me know. First what I will assume. Assume there is bijection. Just assume there is bijection. Yes or no? Assume there is some bijection. Assume there is some bijection. I don't know which bijection. Some bijection. Assume there is some bijection F. Assume there is some bijection F from S to PS. From S to PS, there is some bijection. Okay, then what is your next step? What is your next step? You are assuming some bijection, so take arbitrary bijection. Yes or no? You are assuming there is some bijection, so take arbitrary bijection. So take a arbitrary bijection. Take a random bijection. Okay, so take a arbitrary bijection. Is this clear? Take a arbitrary bijection F. Arbitrary bijection, random bijection, you take F. Then what you will do? Let me know. So you take arbitrary bijection F. I am taking a random bijection. Okay, so let's assume this bijection I am taking. Remember, I am taking this bijection from S to PS. from S to PS, I am giving you a bijection, a random bijection I am giving you. This is your set S that you already know. This is your set S. In this, you have these elements, for example, X1, X2, X3, X4, X5, okay, and so on, X6, and so on. Okay, so this is your set S, and this is your power set of S. Okay, so tell me one thing. This is your power set of S. Let's assume here your power set of S. This is the power set of S. Let's assume. Okay, this is the power set of S. Now, what I'm saying? I am saying take arbitrary bijection. Take arbitrary bijection. What is this F? This F is arbitrary bijection we are taking. Arbitrary bijection that we have assumed. Because we are assuming there is some bijection. We are assuming there is some bijection. So take a random bijection. Yes or no? Is this clear? Please tell me. See, very simple point. You have infinite set S. This is your set X1, X2, X3. This is infinite set. This can be uncountable or countable, whatever. This is infinite set. Now, we need to prove. What we need to prove? We need to prove there is no bijection from S to PS. So we will prove it using Cantor's diagonalization idea. Okay. For that, what we will do? We will prove by contradiction. First, we will assume there is bijection. Just assume there is some bijection. Assume there is some bijection. Now, you take arbitrary bijection. I am taking arbitrary bijection from S to PS. Okay. If this is a bijection, then what should happen? This element should map to someone, yes or no? This element should map to someone. Tell me, in this PS, what elements you have? Every element is a what? In this PS, every element is what? In this PS, every element is what? It is subset of S. Yes or no? In this PS, every element is subset of S. Agree or not? In this PS, every element is subset of S. So tell me, X1 will map to someone. Okay, to whom should I map? Let me know. Just give me something. To whom should I map? Let me know. Give me something random. Give me something random. To whom should I map? Let's assume you are mapping it to, let's assume you are mapping like this. Okay, let's map it to X2, then X4, then X6, then X8, and so on. Okay, let's assume this is mapping like this. X2, X4, X6. Is this a subset of S? Is this a subset of S? Tell me. Is this a subset of S? Yes, this is a subset of S. Okay, so remember, yes, this is subset of S. You can notice, please notice this. This is subset of S. This is subset of S. So yes, this belongs to power set. This belongs to power set of S. Okay. Now, so let's assume this mapping you have. X2 will also map to someone, right? Agree? X2 will also map to someone. Some random bijection I'm giving. Some random bijection. Let's assume it is mapping to phi. Let's assume it is mapping to phi. Yes or no? Let's assume it is mapping to phi. Is this a subset of S? This phi. Is this subset of S? Yes. Let's assume X3 is mapping to whom? Tell me. X3 is mapping to whom? Give me something. Give me something random. Give me something random. So let's assume this is mapping to X1, X7, X9. Okay. This is mapping to this. Tell me, X4 is mapping. Let's assume X4 is mapping to S itself. Let's assume X4 is mapping to S itself. S itself. Okay. Let's assume X5 is mapping to what? Let's assume X5 is mapping like this. X2, X4, X5, X7. Okay, something. So let's assume it is mapping to this. Let's assume X is mapping to what? X6. That is also mapping to, let's assume, X1, X3, X5, X7, and so on. So like this. So some random bijection I've given to you. Yes or no? You can randomly take. See, you can randomly take whatever you want. You can take any random bijection. Take any random bijection, no problem. Okay, take a random bijection. I am giving you a random bijection. Is this clear? So far, is this clear? Tell me. Now, in the diagonalization idea, what we do? So we have taken this random bijection. Remember? This we have taken. Okay, we have taken a random bijection. We have taken a arbitrary bijection. Arbitrary random bijection we have taken. Arbitrary bijection from S to N. From S to PS. We have taken arbitrary bijection from S to PS. This is what we have done. Now what we do? Now what we do? Now in the Cantor's diagonalization proof, what we do? Let me know. What is the next step? Now, in diagonalization idea, what we do? In the diagonalization idea, what is the next step? Tell me. In this diagonalization idea, what is the next step? Create element which does not have any preimage. Very good, very good. Okay, so in this, what you do? Create some element, create some element, let's call it D. Let's call it D. Okay, create some element D which has no preimage. Create some element D in the power set of S. Okay, create some element D in the power set of S. So create some element D in the power set of S which is not covered by this bijection. Which is not covered by this bijection. Yes or no? Which is not covered by this bijection. This bijection is not covering it. Which is not covered by this bijection. Means which does not have any preimage. Yes or no? Which does not have any preimage. Which does not have any preimage. Which does not have any preimage. So this type of element you create. Is this clear? So create this type of element. Can you create? Create this type of element which is not covered, which you did not cover, in this bijection. In this bijection you did not cover. Okay, let's call this element D. Let's call this element D. So tell me. Now let's cover this element D. Let's create. So tell me what you will do. What you will put in your D. In this set D, what you will do? Tell me. This set D, what it will look like? What it will look like? Let me know. In this set D, for example, you can create like this. See, very simple. You can create like this. You can create like this. For x1, it is mapping to something, right? Yes or no? See, x1 is mapping to it. Okay, now in this you just look at x1. Does it include x1? Let me know. Does it include x1? Just focus on x1. Does it include x1? It does not include x1. So remember, the image of x1 does not include x1. So what I will do in D? In this D, I want to make sure that they are different. I want to make sure this element is different from this element. My element D, this is different from this element. So what I will do? Remember, x1 is mapping to this element. X1 is mapping to this element. So I can say, yes, I will put x1. Very good. Okay, because here you don't have x1. So I will put x1. Now tell me one thing, a very simple thing I'm asking. As soon as I put x1, if I put x1, what will happen? Whatever D I create, that will be different from this element. Yes or no? Agree with me? Please understand. Please understand. Now, whatever D I create, whatever D I create, that will be different from this. That will be different from this. Yes. Now tell me what I will do next. Now go to x2. Now go to x2. Does it include x2? Image of x2. This is image of x2. Does it include x2? Image of x2. Does it include x2? No. So what I will do? I will put x2. I will put x2. Is this clear? Because image of x2 does not include x2. So I will put x2. I will put x2. Tell me for x3. Image of x3. Does it include x3? Now go to x3. Go to x3. Image of x3. Does it include x3? No. So I will put x3. So I will put x3. Now tell me next. Image of x4. Does it include x4? Image of x4. Does it include x4? Image of x4. Does it include x4? Yes. So I will not put it. So I will not put it. Okay. Next. Tell me image of x5. Does it include x5? Image of x5. Does it include x5? So I will not put it. X5 also I will not put. Image of x6. Does it include x6? Image of x6. Does it include x6? No. So I will put x6. And so on. So like this I will create. Like this I will keep creating. Like this, I will create. Like this I will create this set D. Is this clear? This set D I will create like this. So tell me how I am creating D. Did you notice what I did? Did anyone notice what I did? How I am creating this set D? See, I am assuming that you have a random bijection from S to PS. This is your set S. Please notice. This is the set S. In this you have elements like x1, x2, x3, x4, x5. x6, and so on, and so on. Okay, this is your set X. This is your set S. Now, here what you have, here this is your power set of S. Okay, so here we are assuming there is a bijection. We are taking a random bijection, arbitrary bijection. Now, did you notice how I am creating this set D? Did you notice how I am creating this set D? See, this set D I am creating like this. I am looking at to create D. What I will put in D? See, what I will put in D. What I will do? For x1, I will check what are the image. fx1, yes or no? Okay, yes, correct. For x1, I will check what are the image. Now, what I will do? If x1 belongs to fx1, then what I will do? Tell me. If x1 belongs to fx1, this x1, if it belongs to its image, for example, here you can notice, if x1 belongs, for example, here you can notice, please notice, like x4 belongs to its image, yes or no? See, x4 belongs to its image. x4 belongs to its image. So I will not put it in my set D, yes or no? So I will not put it in my set D. If x1 belongs to fx1, then what I will do? Then I will not put it in my set D. In the set D, I will not put it. Okay. What is D? What is D? This is my counter example set. Yes or no? This is my counter example set. Is this clear? This is my counter example set. Agree with me? This is my counter example set. Right? Yes or no? I'm creating a set. I'm creating a set. Okay. This is my diagonalization proof set. Or I can say like this. This is my counter example proof set. Or I can say this is my diagonalization set. Okay. Because this I am creating in the diagonalization proof. So I can call it diagonal proof or diagonal set. This is my diagonal set. I am creating a diagonal set. So what I'm doing, if x1 belongs to fx1, then I will not put it in my diagonal set. Next, what I will do? What I will do? If x1 belongs to fx1, if x1 does not belong to fx1, then what I will do? If x1 does not belong to fx1, if x1 does not belong to fx1, then what I will do? Then x1 I will put in my set D. I will put this x1 in my set D. Okay, so the same thing I will do for x2. The same thing I will do for x2. The same thing I will do for x3. The same thing I will do for x4. The same thing I will do for x5. Yes or no? Like this. Okay, so this is how I am creating the diagonal set. See, okay, so to create diagonal set, to create this diagonal set, okay, I am creating a diagonal set D. This, so to create diagonal set D, this D I am creating, okay, according to the diagonalization proof. So to create this diagonal set D, what I am doing? I am doing this. Okay, what we are doing to create diagonal set D, what we are doing? This is what we are doing. So I am saying that X belongs to D, X belongs to D. When I will put X in D, or I can say like this, or I can say like this. See, okay, what I will do for every element. So this is what I will do for all X in S. This I will do for all X in S. For every element X in S, what I will do? I will do this. If X does not belong to Fx, if X does not belong to Fx, means this X does not belong to its image, then what I will do? Then what I will do? Then I will put it in the set D. I will put it in the set D. Okay, and if X belongs to Fx, X belongs to Fx, then I will not put it in the set D. Okay, this is what I will do for all the elements in S. For all the elements, this is what I will do. So finally, what will happen? So finally, tell me, for finally, what will happen? Finally, this D, this belongs to power set, but it's not covered in this bijection. Yes or no? Agree with me? This D belongs to power set, but not covered in this bijection. In this bijection, this set is not covered. Not covered in F. Is this clear? Please tell me. You can easily notice, for example, this set D. Look at this set D. This D belongs to, you can easily notice this set D. This belongs to power set of S. But this set is not covered. This is not covered in F. This is not covered in F. For example, can you notice this set D, this is different from this element? See, these are different, right? Yes or no? These are different. These are different. This set D, this is different from this also. They are different. This set D, this is different from this also. This is different from this also. So this is different from everyone. This is different from everyone. So this belongs to PS, but it is not covered in this bijection. So this is what I'm saying. So finally, remember, so finally, D, this set that I've created, I have created this set. This belongs to power set of S, but this is not covered in this set, in this function F. Okay. So finally, what I can say, tell me. So F is not a bijection. So F is not a bijection, correct? So F is not a bijection. So F is not a bijection. And remember, this F was arbitrary, right? If you remember, this was random, right? So this will work for every, whatever supposed bijection you take. Okay. Whatever F you take, that will never be a bijection. So F is not a bijection. Okay. So I can say there is no bijection. So there is a no bijection. There is no bijection from S to PS. Did you find this proof interesting? Please tell me. Hence proved. This type of proof we have already seen, if you remember. Cantor's diagonalization idea. This Cantor's diagonalization idea, I hope this has become your favorite. This is very simple. You assume there is bijection, and then you create a counterexample. Then you create some element which is not covered in this bijection. Yes or no? So this is the idea. So very simple. I hope you understood all these things. So this is what we have done. This is what we have done. There is no bijection from S to PS. This is hence proved. We have proved it. Okay. That's it. Is this clear? So this is what we have proved. I hope you understood. You can see. Please tell me, if I take this bijection, then what will be my set D? For example, if I take this bijection, this is your set S, this is your power set of S, this is your set S, this is your power set of S, or I can say this is your set X, this is power set of set X. Now tell me, in this situation, if I take this bijection, if I take this bijection F, now let me know, what will be my diagonal set? I will create a diagonal set. I will create a diagonal set. What will be my diagonal set? Give me my diagonal set. How it will look like? How it will look like? Tell me. If I take this supposed bijection, if I take this random bijection, remember this is a random bijection I am taking. This is a random bijection I have taken. Okay, something random. Now tell me, my diagonal set, I will create some element. I will create some element which you did not cover here, which you did not cover in this F. I will create this type of element. So tell me, will I put X0 in the set D? I will create this set D. In this set D, will I put X0? Will I put X0? No, I will not put X0. See, here you have X0. Okay, you can see X0 belongs to Fx0. You can notice X0 belongs to Fx0. X0 belongs to Fx0. So I will not put X0. Okay, I will not put X0. Remember, I will not put X0. Okay, what about X1? What about X1? Let me know. What about X1? Yes, I will put X1. I will put X1. Why? What is the reason? Because you can notice X1 does not belong to Fx1. X1 does not belong to Fx1, right? X1 does not belong to Fx1. So I will put X1. What about X2? What about X2? X2 also I will put, because X2 doesn't belong to Fx2. X2 doesn't belong to Fx2. So I will put it. Okay, what about X3? What about X3? I will not put X3. I will not put X3. I will not put X3. What about X4? I will put X4, right? I will put X4. What about X5? What about X5? I will not put X5. And so on. And so on. Yes or no? Is this clear? Please tell me. Is this clear? So remember, finally, you are getting this set D. I am getting this set D. So remember, I am getting this diagonal set D. This diagonal set D I will get for this example. For this mapping, I will get this diagonal set. I will not put x0. I will put x1. I will put x2. I will not put x3. I will put x4. And I will not put x5. I will not put x5 and so on. Yes or no? And so on. So like this. This type of set I am creating. I will not put x5. So this is the diagonal set we are getting. You can just easily check. Okay. So you can see if x belongs to fx, if x does not belong to fx, then x will belong to D. If x belongs to fx, then x does not belong to D. So what is your diagonal set? Let me know. So can I say your diagonal set is like this? Did you notice? Your diagonal set is like this. I am putting those elements which do not belong to their image. Yes or no? I am putting those elements which do not belong to their image. This is the diagonal set D we are creating. Okay. And you can easily notice this set will not be covered in the F. Okay. You can easily notice one thing, that this D belongs to power set of S. This D belongs to power set of S, but not covered by F. You can take whatever F. Okay. So remember, this set D, this belongs to PS, and this is not covered by F. Okay. So I can say, so there is no bijection. From S to PS. I hope you found this proof interesting. So this is what we have done. Hence proved. Okay. So remember, hence proved. What did we prove? So this is the conclusion. We have proved. Okay, what we have proved? Tell me. We have proved that if S is set, if S is any set, okay, for any set S, what we have proved? We have proved that for any set S, whatever set S you take, there is injection from S to PS. Yes or no? For any set S, there is injection from S to PS. This is what we have proved, right? There is injection from S to PS. We have proved it, that there is injection from S to PS, injective function from S to PS. We have also proved there is no bijection between S, PS. We have also proved there is no bijection from S to PS. Clear? This is what we have done. This is what we have proved. That means what? Tell me, that means what? Now from here, this means what? This means what? That cardinality of S, that is strictly less than cardinality of PS. Yes or no? Cardinality of S, that is strictly less than cardinality of PS. So this is what we have proved, that for any set S, the cardinality of S, that is strictly less than cardinality of PS. And this is called Cantor's theorem. This entire statement, this is called Cantor's theorem. This is known as Cantor's theorem. Okay, that's it. So I hope you found this very interesting. So this is the Cantor's theorem. If S is a set, then cardinality of S, that is strictly less than cardinality of PS. Okay. So for any set A, remember, for any set A, the cardinality of A is strictly less than cardinality of A's power set. Okay. The cardinality of power set of X exceeds cardinality of X. So this is the Cantor's theorem. I hope you understood. These are the statements. So did you understand? Please tell me. This is very important theorem. So this is the conclusion you have to remember. We have proved it. I have given you the proof, but this is the conclusion we have to remember. That S is any set. Finite, infinite, countable, uncountable, whatever. Okay, whatever set you take, remember. Whatever set you take. Finite, infinite, countable, uncountable, whatever set you take. The cardinality of S, that will be strictly less than cardinality of PS. This is the Cantor's theorem. And this is very important. Okay, so let's see some questions. Before looking at the questions, We will see the consequence of Cantor's theorem. Let's see the consequences of Cantor's theorem. And this is the consequence, infinite levels of infinity. This is the consequence we will get, infinite levels of infinity. Did you notice one thing? Did you notice one thing? See, from Cantor's theorem, what will happen? Just tell me. Because of Cantor's theorem, what will happen? These are the consequences of Cantor's theorem. If you take this set n, set of natural numbers, if you take this set n, then what will happen? Can I say cardinality of n that will be strictly less than cardinality of Pn? Let me know. Cardinality of n that is strictly less than cardinality of Pn. Okay, yes or no? Yes or no? Because of Cantor's theorem. Now you tell me. Now you tell me. Let's call it S. Now you consider this as S. Now you consider this as S. So can I say this cardinality of S that will be less than equal to what? That will be strictly less than what? That will be strictly less than what? Let's assume this is set S. Let's call it set S. Then cardinality of Pn that will be less than what? That will be power set of n. Yes or no? Okay. Now what you do? Now you consider this as now you consider this as set A. Let's consider this as set A. Then what will happen? Then what will happen? If you consider this as set A, then what will happen? Then I can say the cardinality of A that will be less than cardinality of power set of A. Power set of A. Correct? Power set of A. And so on. Did you notice? And so on. You will get infinite levels of infinity or not? You will get infinite levels of infinity. You will get infinite levels of infinity. See what will happen. See, this is the level where this is your LF0 level. This is your LF null level. Look at this. This is your LF null. Yes or no? This is your LF null. Means here what you have, tell me. Here what you have, here you have countable infinite. Yes or no? Here you have countable infinite. Here you have countable infinite sets. Okay, for example, set of natural numbers, set of integers, set of rational numbers, sigma star. These things you have here. Yes or no? This is the lowest level of infinity. Then you are getting infinite levels. Agree? You will get infinite levels. See, you will get infinite levels. How? On this level, your power set of n. On this level, your power set of n. On this level, your power set of n. Inception. The movie Inception, if you have seen. Yes or no? Then your power set of n. Is this clear? And so on. Infinite levels of infinity you got. Is this clear? Please tell me. So if someone asks you, can you prove there are infinite levels of infinity? Can you prove it? So we have proved that there are infinite levels of infinity. Isn't it amazing? We have proved. Now you know the proof. We have proved. Remember, you know the proof. If someone asks you, prove that there are infinite levels of infinity. Can you prove it? Yes. So we have proved there are infinite levels of infinity. There are infinite levels of infinity. There are infinite levels of infinity. Okay, there are infinite levels of infinity. Is this clear? And what is the lowest level? What is the lowest level of infinity? Tell me. This lowest level of infinity, what is that? The lowest level of infinity. That is countable and infinite. Yes or no? That is countably infinite sets. Infinite sets. Okay. This is the lowest level of infinity. Countable infinite sets. Like set of natural number, set of integers, set of rational numbers. Okay. Like your sigma star, like your n cross n. Okay. So these things. So this is your lowest level of infinity. This lowest level of infinity we denote by LF null. We denote by LF null. This is the lowest level of infinity. Yes or no? Is this clear? And what about the remaining levels? What you can call them? What about the remaining levels? All these remaining levels, these are called uncountable. Yes or no? The remaining levels, these are called uncountable. All of them are uncountable. Is this clear? The remaining levels, all of them, all these remaining levels, they are uncountable. So I hope you understood. So remember, this is the consequence of Cantor's theorem, that there are infinite levels of infinity. Now, did you find this Cantor's theorem interesting? That this is interesting theorem. Because of this theorem, because of this result, you can create infinite levels of infinity. Because of this theorem, you can create infinite levels of infinity. This is what you can do. So you can see this. This is a Stanford slide. So look at this. By Cantor's theorem, I can say the cardinality of n that is strictly less than cardinality of Pn, cardinality of Pn that is strictly less than cardinality of P of Pn, and so on. So you can see there are infinitely many infinities. See this. There are infinitely many infinities. Your infinite levels of infinities. There is no biggest infinity. Yes or no? Yes or no? Because this will keep going. This will keep going, keep going, keep going. There is no biggest infinity. You don't have any biggest level of infinity because there are infinite levels of infinity. You can see not all infinite sets have same size. Yes or no? Not all infinite set, they have same size. So this is the idea. I hope you understood. Now let's see this question. Tell me the answer for this question. Tell me the answer for this question. Let's see this question. Tell me the answer for this question. If set S is infinite, what is the relationship between S, cardinality of PS? Is it ever possible? Is it ever possible? Is it ever possible? This is never possible for any S. See, this is never, please understand, this is never possible. This is never possible for any S. For any S. For any set S. Okay, any set. You can take any set S. Finite, infinite, countable, uncountable, whatever. Finite, infinite, countable, uncountable. Whatever set you take, countable, uncountable. Whatever set you take, this is never possible. Yes or no? And what the relationship? What the relationship? The relationship that will be cardinality of S that is strictly less than cardinality of PS. Okay? So very simple idea. Now tell me the answer for this question. For every infinite set S, PS is uncountable. What about this? Is this true or false? Think about it. For every infinite set S, for every infinite set S, I am saying for every infinite set S, PS is uncountable. Tell me. For every infinite set S, PS is uncountable. Yes, this statement is true. This statement is true because remember, you have set S. So you know that cardinality of S that is strictly less than cardinality of PS. Yes or no? Now, what is the minimum level of S? Tell me, what is the minimum level of S? S is infinite set. S is infinite set. Okay, so the minimum level of S that is your countable infinite. Very good. The minimum level of S that is countable. So you can say that, okay, see, this is an infinite set. So can I say cardinality of S that is greater than equal to LF null? Agree with me? Yes or no? This is the definition of infinite set. If someone asks you definition of infinite set, what you will say? If someone asks you definition of infinite set in future, if someone asks you what is the definition of infinite set, what you will say? To show off. If you want to show off, then what you will do? Definition of infinite set. I can say S is infinite if and only if S is infinite set if and only if the cardinality of N, the cardinality of S that is greater than or equal to LF null. Yes or no? Agree? Okay. So, or I can simply say the cardinality of S that is greater than or equal to cardinality of N. So like this you can do. Now you tell me. So can I say that this will happen? Okay. So finally I can say that cardinality of N that is less than, I can say that is less than equal to cardinality of S, and that is strictly less than PS. What that means? What that means? Yes or no? See, S is infinite. See, very simple question. S is infinite. This is given to you that S is infinite set. S is infinite set. Now from here, what this means? This means that cardinality of N that is less than or equal to cardinality of S. Okay. Now finally I can say, now this is the equation we have. By Cantor's theorem, what Cantor's theorem says? What Cantor's theorem says? By Cantor's theorem, I can say cardinality of S that is strictly less than cardinality of PS. So finally I can say that just, okay, from these two equations, what I can say cardinality of N that is less than equal to cardinality of S, and that is strictly less than cardinality of PS. Okay. And from this equation I can say cardinality of N that is strictly less than cardinality of PS. That is strictly less than cardinality of PS. What this means? Just tell me. From this equation, this is what we got. That cardinality of PS that is greater than cardinality of PS that is strictly greater than cardinality of N. That means PS is uncountable. That means PS is uncountable. Yes or no? Agree with me? So this statement, remember, this statement is true. For every infinite set S, the power set will be uncountable. The power set will be uncountable. Now tell me the answer for this question. If I say for every set S, now tell me the answer. If I say for every set S, what about this? For every set S. Now this statement is false. Now this statement is false. And what is the counterexample? Counterexample is any finite set. Yes or no? What is the counterexample? Counterexample is any finite set S. Any finite set S is your counterexample. Is this clear? Is this clear? Because if you have finite set S, see, for finite set S, what will happen? For finite set S, what will happen? PS will also be finite. Yes or no? PS is also finite. PS is also finite set. So very simple. So this statement is false. Now let's move on. Tell me the answer for this question. P of N is uncountable. Power set of N that is uncountable. Power set of N. Power set of N. That means 2 power cardinality of N. This is uncountable. Yes, this statement is true. Okay, because you know that cardinality of N that is strictly less than cardinality of Pn. Okay, and this is the definition of uncountable. So very simple. Tell me the answer for this question. For any sigma, this is your alphabet. This is your alphabet. By definition, alphabet is finite, non-empty set. Yes or no? By definition, this is finite, non-empty set of symbols. Correct? This is finite, non-empty set of symbols. So tell me, what is sigma star? Let me know. What is sigma star? I want to know what is sigma star. For any alphabet, what is sigma star? What is sigma star? What is sigma star? See, sigma star is set of all strings. Yes or no? This is set of all strings. And by default, strings, they have finite length. Yes or no? In this sigma star, do you have infinite length strings? Do you have strings of infinite length? No. All of them, they have finite length. Yes or no? All of them, they have finite length. That you already know. So sigma star, this is set of all strings. This is set of all strings over sigma. So remember, this is set of all strings. Please understand that sigma star is set of all strings. This sigma star, remember, this is set of all strings like epsilon. Okay, if you have, for example, if your alphabet is like this, then your sigma star has strings. Your sigma star has strings, remember. Your sigma star is set of all strings. What you can say about sigma star? We have already seen that sigma star is countable infinite. Yes or no? We have already seen this is countable infinite. This we have already seen. This is a countable infinite. And what about what is sigma? What is power set of sigma star? You know what is sigma star. Then what is power set of sigma star? What is power set of sigma star? Let me know what is power set of sigma star. What is it? This is set of strings. This is set of what? Tell me. This is set of what? See, this sigma star is set of strings. Please understand that this is set of all strings. This is set of all strings. Correct? The sigma star is set of all strings. What is 2 power sigma star? Means what is power set of sigma star? A simple question I am asking. What is power set of sigma star? Just apply the definition of power set. Just apply the definition of power set. Just apply the definition of power set. You will have those things which are subset of sigma star. You will have those things which are subset of sigma star, right? Yes or no? You will have power set of sigma star. It will have those things which are subset of sigma star. Subset of sigma star, what that means? Subset of sigma star. If A is subset of sigma star, then A is a language. Yes or no? Then A is a language. Agree? This is the definition of language. This is the definition of language. Every language is subset of sigma star. This is the definition of language. Every language is subset of sigma star. Every language that is subset of sigma star. So can I say this is set of all languages? This is set of all languages. Yes or no? This power set of sigma star. This is set of all languages. This is set of all languages. And you can notice one thing. So first of all, this is set of all languages. This is set of all languages. All the languages you have in this. In this power set of sigma star, you have all the languages. For example, what you have in this power set of sigma star, what you have, let me know. In this power set of sigma star, give me some languages which you have. For example, in this power set of sigma star, you have this language WW also. You have A power and B power and this language also. You have this language also. You have ending with A. This language also you have. Okay, yes or no? Like this and so on. Okay, your A power prime, this language also you have. Your halting problem of Turing machine. Halting problem of Turing machine, that also you have. Acceptance problem of Turing machine also you have. Agree? Okay, I can say, what else? A lot of, okay, LD, you know, LD, diagonalization language, that also you have. So basically, power set of sigma star, this is set of all languages. This is set of all languages, remember. This is set of all languages. Now you tell me one thing. You know that cardinality of sigma star, that is strictly less than what? That is strictly less than what? That is strictly less than cardinality of power set of sigma star. Now this is your countable infinite. This is your countable infinite. So what will be power set of sigma star? This is countable infinite. Countable infinite. This is your LF null. This is your LF null. So what will be power set of sigma star? What will be power set of sigma star? That will be uncountable. So set of all languages, what is that? Tell me. So remember, this is countable infinite. This is countable infinite. And what is set of all languages? And what is set of all languages? This is uncountable. How many languages are there? Tell me. How many languages you can create? How many languages you can create? Uncountable. Uncountable number of languages you can create. Uncountable infinite. If someone asks you how many languages are possible, okay, if you have any sigma, for any sigma, how many languages are possible? For any sigma, I can say, what is the number of languages possible? Tell me. What is the number of languages possible? How many languages are possible? What is the number of languages possible? That will be uncountably infinite. That will be uncountably infinite. Yes or no? or I can say that is uncountable. That is uncountable. That is uncountably infinite. Is this clear? Please tell me. And how many strings you can create? How many strings you can create? How many strings you can create? Tell me how many strings you can create. That will be countably infinite. That will be countably infinite. Is this clear? Please tell me. So I hope you understood this. Now let's see this question. Tell me the answer for this one. For any sigma, what is sigma star? Sigma star is countable. Can I say? Is this true or false? Sigma star is countable. Yes, this statement is true. Okay. This statement is true. What about this question? Tell me. For every sigma, power set of sigma star. Remember what is power set of sigma star? This is set of all languages. Remember, this is set of all languages. This is set of all languages. This is uncountable. Yes, this is true. Yes, this statement is true. Let's move on. Tell me the answer for this question. This is the same. Set of all languages. Set of all languages is uncountable. Yes, this is true. Set of all languages is uncountable. This is true. What about this question? Tell me the answer for this question. S is power set of set A. Remember, set S is power set of set A. If S is infinite, then S is uncountable. Is this true? Is this true? This statement. S is power set of set A. If S is infinite, then S is uncountable. Think about it. Is this statement true or false? Yes, this statement is also true. Why? What is the reason? Give me the reason. Give me the reason. Give me the reason. See, if remember S is power set of A. Remember, this is given to you that S is a power set of A. You tell me, if S is infinite, can I say A is infinite? If S is infinite, can I say A is infinite? Let me know. If S is infinite, can I say A is also infinite? Then A is also infinite. Yes or no? Then A is also infinite. If S is infinite, then A is also infinite. So what you have? Now A is infinite. So now you have this, that A is infinite set. You have this, that A is infinite set. Okay, A is infinite set. That means what? That means what? That means cardinality of A that is greater than equal to cardinality of N. Yes or no? Because A is infinite set. So cardinality of A that is greater than equal to cardinality of N. And you already know that S is power set of A. S is power set of A. So I can say that cardinality of A that is strictly less than cardinality of S. Yes or no? This equation you got. From this equation, I can say cardinality of N that is strictly less than cardinality of S. So finally, I can say that S is uncountable. S is uncountable. S is uncountable. Is this clear? Did you understand this question? Set S is power set of A. If S is infinite, then S is uncountable. Okay? If S is infinite, then S is uncountable. See, something interesting you can notice means a power set is infinite if and only if it is uncountable. Did you notice? Did you notice? When will a power set be uncountable? Or I can say, when will power set be infinite? So you can notice a power set. A power set, remember, power set. A power set is uncountable, is infinite. When can I say a power set is infinite? A power set is infinite if and only if it is uncountable. It is uncountable. Agree? Yes or no? Did you understand this? See, a power set, you can see S is power set. This is what you can see. S is power set. S is power set. Now, if it is infinite, then it will be uncountable. This is what we have seen. S is power set. If it is infinite, then it will be uncountable. So can I say this statement is true that you already know? This statement is true. This statement is true that you already know. Correct? Okay. So this statement is true. So can I say power set can never be countable infinite? So did you notice that power set can never be a countable infinite. Did you notice? A power set is never countably infinite. Is never countably infinite. Agree? Is never countably infinite. Interesting result, right? Yes or no? A power set is never countably infinite. If you take power set of any set, that is never countably infinite. That is never countably infinite. Because if power set is infinite, then it will be uncountable. So you can see this. A power set is infinite if and only if it is uncountable. Please tell me, did you understand? Let me know. This, did you understand? Did you understand this? Because simple points. This was our question. This is our question. Set S is power set of A. If S is infinite, then S is uncountable. We have proved it. You can see this proof. From this proof, you can see that S is uncountable. So this is what I'm saying, that if power set is infinite, then it is uncountable. You can see if a power set is infinite, then it is uncountable. So I can say power set is never countably infinite. This is what we can say. So remember, power set of any set, is never countably infinite. Yes or no? Is never countably infinite. Is never countably infinite. This is what we can say. Power set of any set that is never countably infinite. Understood? Let me know. Let's see this question. Tell me the answer for this one. Let me know the answer for this one. A power set. Okay, I am saying power set is infinite if and only if it is uncountable. A power set is infinite. Power set is infinite if and only if it is uncountable. Yes, this is true. Yes, this is true. Okay, so the result is very simple. See, power set of any set, is never countably infinite. Is never countably infinite. Countably infinite. Okay, let's move on. Tell me the answer for this question. Let me know. Union of set A, set B is uncountable. This is given to you. Union of set A, set B, that is uncountable. Then what is a possibility? Which of the following is a possibility? A union B is uncountable. This is given to you. A union B, that is uncountable. This is uncountable. Is it possible? Is it possible both can be countable? Is it possible both can be countable? No, this is never possible, right? Yes or no? Because if both are countable, then countable union countable is countable. Yes or no? So clearly I can say, so both A comma B cannot be countable. Both A comma B countable. Both A comma B countable, not possible. Both A comma B countable. This both A comma B countable is not possible. Is not possible. This is not possible, remember. Okay, this is not possible. At least one of them must be uncountable. At least one of them must be uncountable, right? At least one of them must be uncountable. Must be uncountable. Must be uncountable. So finally I can say which is a possibility? Both uncountable. Yes, this is possible. This is possible. This is possible. These are possible. Okay, let's move on. Tell me the answer for this question. Countable union uncountable. That is uncountable. That is uncountable. Okay. In uncountable, if you do something, if you add something, in this uncountable, if you add something, does not matter. The result will be uncountable. Okay. Tell me the answer for this question quickly. Set of all finite subsets of n. This we have already seen. Set of all finite subsets of n. Set of all finite subsets of n. This we have already seen. This is countable. We have already seen in the last lecture. In the previous lecture, we have already seen. Yes or no? Yes or no? Previous lecture, we have already seen. In the previous lecture, we have already seen. Now tell me the answer for this question. See, one interesting thing I want to tell you. This we have already seen that set of all finite subset of n, that is a countable, right? Okay. And what about set of all subsets of n? What about set of all subsets of n? What about set of all subsets of n? Tell me, what about set of all subsets of n? Set of all subsets of n. First of all, set of all subsets of n. What is that? What is that? Set of all subsets of n. Set of all subsets of n. This is power set of n, right? Yes or no? Set of all subsets of n. This is your power set of n. Yes, this will be uncountable. This will be uncountable, right? Correct? Okay. Because you can easily notice that power set of n, cardinality will be strictly greater than cardinality of n. Okay. So you can see. So this is uncountable. Now let's move on. Now you tell me one more thing. What about set of all infinite subsets of n? Set of all infinite subsets of n. Infinite subsets of n. What about that? Set of all infinite subsets of n. I am asking set of all infinite subsets of n. What do you think? Set of all infinite subsets of n. Set of all infinite subsets of n. Can it be countable? Can it be countable? If it is countable, then set of all subsets will be countable. If this is countable, then set of all subsets will be countable. So this will be uncountable, right? Yes or no? Please notice, because remember, this will be uncountable, correct? What is the reason? This will be uncountable. What is the reason? The reason is simple. The reason is simple. What is that? See, set of all subsets. Notice, what is set of all subsets? What is set of all subsets of n? Tell me, what is set of all subsets of n? This is union of two things. Union of set of all finite sets, subsets, set of all finite subsets, set of all finite subsets of n, set of all infinite subsets of n. Yes or no? Set of all infinite subsets of n. Infinite subsets of n. Agree? Is this clear? So you can see this set of all subsets of n, set of all subsets. This is your power set of n. And this is union of two things. This is union of two things. Set of all finite subsets of n, union. Set of all infinite subsets of n. We already know this is countable, right? Yes or no? We already know this is countable. We already know this is countable infinite. This is countable infinite. And we already know this is uncountable. We already know this is uncountable. This we already know. This is uncountable. So what this will be? Now what this will be, let me know. Please tell me. See, set of all subsets, that is union of two things. We already know this is countable infinite. And we already know Pn is uncountable. So what will be this set of all infinite subsets? This will be uncountable. Very good. This also will be uncountable. Okay, so take care. Is this clear? Every question they can ask you anything. They can ask you anything, so you can solve it. Tell me the answer for this question. Let S be any countable set. Let S be any countable set. Any countable set. Let S be any countable set. Then set of all finite subsets of S. Set of all finite subsets of S. Set of all finite subsets of S. Yes, that will be countable. Okay, just like n. Just like n. Agree? Yes or no? So just like n. Very simple. So if you have any countable set, then set of all finite subsets of n, that will be countable. Okay. Tell me the answer for this question. Tell me the answer for this question. Let S be any uncountable set. S itself is uncountable. S itself is uncountable. S itself is uncountable. Now tell me, set of all finite subsets of S. Now tell me, set of all finite subsets of S, that will be countable or uncountable? Set of all finite subsets of N, S. Yes, that will be uncountable. Very good. Why? Tell me why. Tell me why. See, S is uncountable. You are saying that S is uncountable. You are saying that S is uncountable. And can you notice that if you take even the finite subsets, if you take, for example, this S is uncountable. See, this is your S, A1, A2, A3, A, and so on. This itself is uncountable. See, notice, this itself is uncountable. This itself is uncountable. Now you notice, if you see all the finite subsets of N, just look at all the finite subsets of N. All the finite subsets of S. What that will be? All the finite subsets of S. So at least you will have, okay, that will be as big as, yes or no? At least these elements will be there. See, this is a finite subset of S. Did you notice? This is a finite subset of S. This is a finite subset of S. So can I say set of all finite subsets of S, that also will be uncountable? Or you can take the real number. For example, real number is uncountable. The set of real numbers is uncountable. Okay, this itself is uncountable. Now if you take set of finite subsets of R, set of finite subsets of R, if you take set of finite subsets of R, okay, just take the finite subsets of R, then that also will be uncountable. Okay, because what you will have? Because what you will have? You will have every finite subset. Every finite subset you will have. Okay, yes or no? So can I say set of all finite subset of R, that also will be uncountable? Because this will be at least as big as R. Yes or no? See, this will be at least as big as R. Agree with me? This will be at least as big as R. This set. I can say this is at least as big as R. Agree with me? At least as big as R. So I can say this also will be uncountable. Is this clear? So if S is uncountable set, then set of all finite subsets of S, that also will be uncountable. Very simple. Now tell me the answer for this question. Let me know. S is countable set. Okay, this we have already seen, but this is important. S is countable set. This can be countable, finite or infinite. Remember, S is countable set. S is countable set. This can be finite or countably infinite. This can be finite or countably infinite. Okay. So if S is any countable set, finite or countably infinite, then set of all finite subsets of S, that will be countable. Okay. So very simple. These things we have already seen. So this is a note. You can see, if S is any countable set, if S is any countable set, remember, when I say countable, then this can be finite or this can be countably infinite. Okay, then set of all finite subsets of S, that will be countable. That will be countable. Okay. So let's see. This is one last, another important consequence, okay, of Cantor theorem. This is the last consequence. Another consequence, that is set of all subsets of infinite set is uncountable. Yes or no? This is last consequence of Cantor's theorem. This is saying that set of all subsets of any infinite set is uncountable. Means if S is uncountable, if S is uncountable, sorry, if S is infinite, if S is infinite, notice what this is saying. This is saying set of all subsets of any infinite set, any infinite set. So if S is infinite set, okay, then what you can say about set of all subsets of S? What you can say about set of all subsets of S? Set of all subsets of S, that is your power set of S. That is your power set of S. Now S is infinite. S is infinite. So this power set of S, this will be uncountable, right? Yes or no? this will be uncountable. This will be uncountable, right? Correct? Because set of all subsets of S, that will be power set of S. That will be power set of S. See, S is infinite. What that means? What the definition of infinite set? Means cardinality of S, that is at least as big as N. Okay, that is at least as big as N. Okay. And you already know that cardinality of S, that will be less than cardinality of PS. That will be strictly less than cardinality of PS. Okay. And you can also see this. So from here, what you can say? From these two, what you can say? From these two, I can say cardinality of N, that is strictly less than cardinality of PS. So what is PS now? So what is PS now? So PS is uncountable. Yes or no? So PS is uncountable. Is this clear? So PS is uncountable. So this is the final point. The set of all subsets of any infinite set is uncountable. Set of all subsets of any infinite set is uncountable. And this is important. Did you understand this? Please tell me. Did you understand this? Did you understand this? Set of all subsets of any infinite set, that is uncountable. And this is your proof. You can easily see the proof. So if you have any infinite set, then set of all subsets, that will be uncountable. Okay, that's it. So this is your chapter. This is your Cantor's theorem. Did you understand Cantor's theorem? Please tell me. Let's see this question also. Tell me the answer. If S is power set of A, S is power set of A, S can never be countably infinite. Is this true or false? S is power set of A, S can never be countably infinite. This we have seen, this is true. This we have already seen. This we have already seen, this is true. Okay. So this is your chapter. We have seen Cantor's theorem. Please tell me, did you understand Cantor's theorem? Let me know. Did you understand Cantor's theorem? Please tell me. We have seen what is Cantor's theorem. What are the consequences of Cantor's theorem? Some questions we have seen. All the variations we have seen. The proof we have seen. Proof of Cantor's theorem using diagonalization idea. That also we have seen. So please tell me, did you understand Cantor's theorem? What is Cantor's theorem? What it says? And what are the consequences? What are the questions possible? What are the variations possible? Please tell me, did you understand? Let me know. Did you understand everything? Please tell me. Are you comfortable with Cantor's theorem? Very simple theorem, but very nice questions can be created. From this Cantor's theorem, a lot of nice questions can be created. Okay. So we have seen the proof, we have seen the variations, we have seen the questions, everything we have seen. Now one last topic is remaining, and that is countability results for languages. This is in the next session, we will see this countability results in theory of computation, means countability results for languages. Okay. So this is what we will see in the next session. And then we will see all the GATE, TIFR, NET, NILIT, ISRO, all these exam PYQs. Okay. Previous year exam PYQs. So this we will see in the next session. Okay. I hope you understood so far everything. So far everything that we have seen, I hope you understood. Okay. So on the Go Classes YouTube channel, please comment and share your feedback. All the countability lectures. Okay. The countability playlist, the complete countability playlist, that is available on the Go Classes YouTube channel. So on the Go Classes YouTube channel, please comment and share your feedback. Okay. Like, comment, share. Okay. Okay. Thank you, everyone. So in the next session, we will see this last thing, that is countability results. Some results we will see for languages in theory of computation, right? Okay. And then we will see some questions. Okay. Thank you, everyone.